Alright guys, this is Zachary, one with Clean Code Studio. Clean Code, Clean Life. Today we're going to continue our lesson on solid principles. Specifically, we're going to go on to the second principle, which is O. A class or entity should be open for extension, but closed for modification. During this lesson, we will start to understand the open-close principle by inverting dependencies and refactoring extensible behavior behind interfaces. So guys, come along with me today as we dive in and start to understand the open-close principle in depth.
Step 1, we're actually going to implement the open-close principle incorrectly. So this is incorrect implementation. So let's take the use case that our boss says we need to create triangles. Or actually, let's start with squares. We need to create squares and we have to model them. So square has a height, technically it'd be one side, but for the purpose, let's just do height and width, right? Next, our boss comes to us and says, hey, we need to calculate the area of any given number of squares. So, following the single responsibility principle, we simply create an area calculator class. Now this area calculator class has a single method, and we're going to call this public function calculate. We're going to call it squares, just like that. And now all that this calculate method is going to do is going to take any given number of squares, right? And we're going to loop through those squares just like this. And we're simply going to say, okay, our area equals square width times square height, which is the formula to get the area of a square. And then we're going to return array sum of area. And that gets us the area for the combined amount of squares area. So we just get the area for the total number of squares. But next, our boss comes to us and says, okay, hey, we're adding a new shape in. We're adding a circle. Now all we need for a circle is the radius. But we also need to be able to calculate the total area of any number of shapes, not just squares. So it can be a combination of squares and circles. So we refactor this, and we'll just say, okay, that's not too hard. This is we'll just change that to shapes, make this shape, and then we'll do if is a, and we'll do shape square. Then we'll calculate the shape this way, which is the formula to get the area of a square. Else, if is a shape circle, then the area is going to need to get the formula for the circle, which is going to be shape radius times shape radius, put some parentheses around that, and then do times pi. So now we're properly saying, okay, if we have squares and we have circles, we can properly calculate the total area for any number of shapes. But then your boss comes back, he's like, hey, we need to add in a triangle. We need another shape, we need a triangle. Well, as you can probably see, this is starting to get a little unwieldy. So then we're going to do public base for triangle and public height. So now we need to do another else if in here that says else if is a shape and then triangle, then the area is going to equal the shape height times the shape base divided by 2. And let's just go over here, add more parentheses. And now we're properly calculating the area for square, circle, or triangle. But as you can see, guys, we've had to modify our code 2 or 3 times now. This is not a good example of open for extension, closed for modification. In fact, this is the exact opposite. This is how you incorrectly implement the open-close principle. So let's move on and let's focus on how we can refactor this code to properly implement the open-close principle. So you guys may remember this quote from earlier by Uncle Bob. We actually showed it on the opening screen. So let's read it now and break it down. When you have a class or method you want to extend without modifying it, separate the extensible behavior behind an interface, and then flip the dependencies. So what does this mean? Well, if we break it down into 2 parts, part 1 being separate the extensible behavior behind an interface. Well, what's our extensible behavior? The calculation of the area. Part 2, then flip the dependencies. All this means is that we need to flip the location of the dependencies from being within if this is the type, calculate the area this way. If this is the type, calculate the area this way. All it means when it says flip is we just need to flip our calculations from the area calculator and put them into the shape classes themselves. So let's actually go through and do that right now. Part 1, separate the extensible behavior behind an interface. So let's create an interface called shape. Our extensible behavior, the behavior we keep having to check if else, if else, if else. If it is this shape, do this, else if it's that shape, do that. That's our extensible behavior, calculating the area. So within our interface, and remember, an interface is just a contract enforcing a class to have or implement a method. So our interface for shape is going to contractually bind classes to implement the area function, public function area. Next, we need to actually flip the dependencies, and this is part 2. So part 1 is put the extensible behavior, which is the calculation of area, behind an interface. Part 2 is flip the dependencies, and all that means is we need to implement the interface on all of these shape classes. And so we can do implements there, implements on circle, and implements on triangle. Notice if we hover over, we'll see this red flag on all of our classes now. And that's because they're implementing the shape interface and they are contractually binded to have the area function, and they do not. Class must be declared abstract or implement method area. So let's actually implement part 2 and flip our dependencies. Public function area. For square, all we're going to do, we're going to take this right here and do return. We're going to return this width, return this height. On circle, public function area, then we're going to take this right here, and all we're going to do is do return pi times this radius, aka pi times radius squared. And then on our triangle, we're going to do the same exact thing, public function area, and then we're going to return shape height times shape base divided by 2. Now, we're actually going to just completely remove all of these if-else's, every single if-else. Next, we are going to go up here to our calculate method, and we're going to say the type passed in, or the types passed in to calculate, all have to be class instances that have implemented the shape interface. So now in our calculate method, this says, hey, any shapes passed in, they have to have the area function. So once we know we have the area function, Well, it's as simple as saying shape area and just pushing into area again. So area equals shape area. And so we properly have flipped our dependencies from this if else, if else, if else structure. And we have flipped the dependencies and encapsulated the area calculation within the given shape class themselves. And we have enforced that they have the area functionality via their interface. So guys, I hope that was helpful. If this was useful, like and subscribe, and next we will be getting on to Liskob's substitution principle.
Simple